The most important feedback factor, positive or negative, is moisture in the air, and its effect is both critical and poorly understood. Everyone agrees that warmer weather puts more moisture in the air, but does it show up as increased humidity, in high clouds, or in low clouds? Some of these may have positive feedback effects, some negative. Most all of the climate models assume that as the world warms, the relative humidity stays constant. Relative humidity is a measure of how much water vapor is in the air compared to how much water the air could contain at a given temperature and pressure, and that carrying capacity increases as the air gets warmer, meaning that warming with a constant relative humidity results in an increase in total water vapor in the atmosphere. It turns out, though, that as we have warmed over the last 50 or 60 years, relative humidity at most levels of the atmosphere has actually fallen off, so that models are actually wrong here. They're overestimating the increase in water vapor from rising temperatures, and thus overestimating the feedbacks in total warming. The other positive feedback effect I want to discuss briefly is methane. Methane is the hot talking point in the catastrophist camp right now. Just do a Google search and you will see all kinds of articles about man-made warming causing methane to be released from melting Arctic tundra, which in turn has warming effect as methane is a much stronger greenhouse gas than CO2. The alarmists are all saying that methane release is accelerating and increasing faster than ever due to man. But this is simply not true. Methane has been increasing true over the last decades, but in fact the rate of change is actually decreasing, not accelerating. It is doing exactly the opposite of what we might expect were the methane positive feedback theory correct. But I said I had a better and more elegant way of getting at feedbacks in the climate sensitivity to CO2. The key is that if certain sensitivity and feedback levels exist going forwards in models, it has to exist backwards in history. Physics that apply in 2050 have got to apply in 1850 as well. If we have strong positive feedback in the future, it had to exist in the past as well. Since we have been measuring CO2 and temperature, however imperfectly, for a century and a half or so, we can extend these forecasts backwards into the past and see how well they explain past warming. We can ask, to believe this 10-degree forecast, what do we have to believe about past warming? And as you can see, we would have to believe that we've already seen 4 degrees Celsius of warming to be consistent with the same assumptions that drive a 10 degrees C forecast. Of course, there's probably a time delay, maybe 10 or 15 years, but this changes the answer only a small amount, by a few tenths. We still find ourselves in the position to support high positive feedback forecasts of having to believe there have been levels of warming way beyond what we have actually observed. Remember I showed you that we had seen perhaps 0.6 C of warming over the last century, and even that may have been exaggerated by measurement biases. And that 0.6 C is for all warming effects combined, so the warming from CO2 is only a portion of that number. So we might expect that the warming of CO2 historically with all these other effects was maybe a couple of tenths of a degree. That means the actual sensitivity curve should go through a point above here, which would put us in the negative feedback zone, which is, by the way, exactly where natural scientists would assume the process operated and would imply a total warming from man-made CO2 over the next 100 years of less than 1 degree C. So the amount of warming we've seen historically is consistent with negative, not positive feedback. But climate scientists say all the time that their models accurately describe past warming. To some extent, this means that they have managed to tweak and tune their models to spit out something like 20th century temperature profile. I was a financial and economic modeler for years, and a typical technique to use was what I called a plug variable, or an arbitrary variable whose value in each period is set to exactly match what one needs to make the model spit out the desired result. For climate modelers, one such plug variable is aerosols. Aerosols are solid and liquid particles in the atmosphere that can reflect solar radiation back into space and thus have a cooling effect on the Earth. They can be of natural or man-made origin. Man-made aerosols typically are byproducts of combustion and industrial activities and include things like sulfur dioxide and soot or black carbon. I'm actually not going to talk much about black carbon as the evidence is increasingly equivocal as to whether its net effect is cooling or warming. I personally believe that black carbon soot from Asia is in part responsible for recent summer melting events in the Arctic. So let's focus on sulfate aerosol concentrations on the left. Sulfate aerosols, unlike CO2, are short-lived, so that they tend to be concentrated downstream of the industrial areas that produce them. These aerosols are concentrated near parts of North America, Asia, and Europe, and cover perhaps 10% of the globe. The appeal of man-made aerosols as a plug figure is that, unlike CO2, we have a pretty good understanding of how to run an industrial economy while limiting the output of these aerosols. Countries like the US are already well on its way to reducing the emissions of these aerosols, and most countries will follow suit over the coming decades. So if these aerosols are assumed to have a large cooling effect today, they can help plug the gap between reality and the hypersensitive climate models, while still allowing catastrophic forecasts as the aerosols and their theoretical cooling effect go away in the future. The IPCC is the first to tell us that scientists really don't have a good handle on the magnitude of aerosol cooling. In a sense, this is a benefit to climate modelers, as it allows them to assume any cooling number they need to make their models backcast accurately. The most telling sign of this is that most modelers nowadays can produce results that look exactly like history, but they all have very different cooling rates for the aerosols. By some strange coincidence, every single modeler has assumed an aerosol cooling rate that is the exact value needed to make his or her model fit history. This is what I mean by a plug variable. But simple logic tells us that these assumptions almost have to be outlandish. Remember, high sensitivity assumptions were overstating past warming by 1 to 3 degrees Celsius, meaning that aerosols cover about 10% of the globe. We would have to see local cooling effects in those areas of about 10 to 30 C to actually produce a global 1 to 3 C cooling. And we can detect no real cooling whatsoever or substantial change in warming trend between aerosol affected areas and those without aerosols. The other explanation for differences between forecasted and past warming is time delays and having heat hide in ways that don't show up in the surface temperature record. These are basically the same argument. The same oceans that may provide a dampening or slowing effect on warming after a change in radiative flux are the only locations where heat may be stored without it appearing in the surface temperature record. I mentioned earlier that scientists added new satellite and floating tools to better measure the heat content of oceans down to 800 meters. Since these tools were first put in place in 2003, we have not seen any meaningful increase in ocean heat content, shown in red here, as compared to the blue upwardly sloping line, which is the change in ocean heat content we might expect from the modelers' high feedback, high sensitivity assumptions were correct. If we really are seeing increased forcings from CO2 concentrations, the heat has to be going somewhere. It can't just go on holiday for a year or 2 or 10, but if we are not seeing it in the surface temperature record, and we're not seeing it in the ocean heat content, it's hard to imagine where it might be hiding. The final test I will discuss for these high sensitivity climate models is to actually compare their forecast with actual temperatures after the forecast was made. This seems like an obvious test, but the IPCC has been pretty clever. They bring out a new 100-year forecast every 5 years and throw out the old one, such that we never really get to test more than the first couple years of a century-long projection. James Hansen, who is head of the NASA GISS and friend of Al Gore and a consultant on his movie, stood before Congress with this chart in 1988. First, he pointed out how well his model matched historic temperatures and used that as proof of the accuracy of his modeling techniques. Of course, a lot of folks in the financial industry have led their investors off a cliff with a similar claim. Second, Dr. Hansen presented 3 forecasts based on a variety of CO2 emission scenarios from low to high emissions. As it turns out, actual emissions have actually exceeded even his high emission case, scenario A, so I have used that one for comparison. So we take his forecast and we find it completely falls apart practically from the first day after his presentation. Current temperatures are not even close to those he predicted. He is off by a factor of 5 or more on temperature increase since his presentation to Congress. Again, the reason is simple. Yes, CO2 concentrations have an effect on world temperatures, but scientists like Hansen have grossly overestimating this effect, in particular because of crazy high assumptions about positive feedback. I and many skeptics don't deny that increased CO2 will have some incremental warming effect in the future, but we expect that effect to be at most a half a degree to 1 degree C over a century. Hansen told Congress we would see that in a decade.